Well, thank you for inviting me, Cole. Thanks for everyone for attending. I hope you'll find the talk interesting. Let me share my screen, jump right into it. Hello, everyone. So my name is Will Crichton, and you might think that I am a postdoctoral researcher in the year 2023, but that's actually not true. I am a systems programmer who's come back from the year 2030. And that's right, in 7 years, we're all still alive. And I've come back in time to give you a quick sense of what programming is like in the future. I'll give you a simplified example from my day job as a back-end engineer. That hasn't changed. Our code base is obviously written in Rust. We all decided in 2025 we've had enough memory vulnerabilities for a lifetime. And what this short example shows is an API client calling into our service. So we've got this API request struct that has some kind of secret and it's calling out to some endpoint specified by a key. We have some code that creates this API request and then we shoot it off and get back some response. Pretty simple, right? And so I'm going along, I'm testing out my application. I say, all right, let's bump open a terminal. Let's run our tests and see if, yep, it's running great, no issues. And then I say, okay, let's double check this is running correctly in debug mode. So I pass an environment variable and I get, some kind of panic, cannot access non-debug endpoint and debug mode. Oh, well, that's annoying. I'll have to figure out why I'm sending the wrong endpoint in this request. If this was 2022, I might start up a debugger, or I might toss in a bunch of print lines everywhere to figure out what's going on. But thankfully, in the year 2030, I could just ask my IDE. I'll say, okay, what code is relevant to the request key at this line? So I'll type that. I activate focus mode in Flowistry. And it says, it turns out it's only these couple lines of code. So we see it depends on this request, and that gets defined by this endpoint, and that's dependent on this debug variable. And say, yep, a little typo, a debug. We can fix that. Thanks, Flowistry. And then if we run our tests again, great, no panics this time. But, also in the year 2030, we get that correct code is about more than just lack of crashes, right? We don't want to leak sensitive data to comply with the UN Privacy Initiative of 2028. And so I like to run my security checker in CI, but I'll do it manually here just for demonstration purposes. So I can type cargo IFC, enter, and we see, we have some kind of insecure flow from secret to log debug. Let's take a look at that. So we create our secret here, and then, it turns out we were logging our request, and that request, the debug representation, includes all the fields, and one of the fields is the secret. And so we were accidentally writing our secrets in plain text to a log. That's definitely not good. So we can fix that. We can change this to, let's just say we log out the request key instead, because that's not, it's not unsafe. And I run cargo IFC again. All right, no security issues found. Isn't that great? That's $1 billion lawsuit we just avoided. All right, and so at this point, you might be wondering, how does any of this work? I mean, obviously can't tell you too many details about the future. That's a time paradox. But lucky for you, the research that went into this was just published a year or so ago. And without further ado, I can talk to you a little bit about the foundational techniques underlying the technologies you just saw in this demo. So let's change the screen share back to the slides. Perfect. So the rest of this talk is going to be about what just happened. What was the problem being solved, and how exactly does that tool work? Briefly, I'll do a quick acknowledgement, which is the theory underlying the tool was done jointly with Marco Petrignani at the University of Trento and my PhD advisors at Stanford, Pat Hanrahan and Manish Agrawala. And the programming team was myself and Connor Fogarty, who's an incoming freshman at Stanford. All right. So the core idea here is this concept that I call information flow, which you can understand intuitively as, can some piece of code influence some other piece of code? And so in this scenario, right, you construct some value, like we have this API request, and then when the program executes, you run into a bug. You say cargo run invalid request key. And the process of debugging is usually to start at the observable problem and work backwards to the root cause. So we would ask, what defines that request key, right? And what pieces of code influence it? And the rough flow of influence is shown here in these red arrows. So the key in the request comes from this struct definition. That key comes from this variable endpoint. That endpoint gets defined up in the middle of the program. That endpoint is influenced by this mutation. That mutation is conditioned on this debug variable, and then that debug variable gets defined all the way up at the top. All right, there we go. These arrows show the information flows between the different parts of the program, but this isn't a particularly good visualization of the information flows. I would say a more standard one looks like this, where all the lines of code that don't have an information flow to or from the request key get grayed out. This is more commonly called the slice of the program. And so the tool that I showed you is computing the information flow between all the instructions and variables in the Rust program, and then only showing the subset that can affect a given variable. And so the goal of this talk is to explain how the tool works. First, I'm going to give you a precise definition of information flow, so we understand what it means for one variable to depend on another. And then I'm going to explain how Flowistry finds information flows in Rust programs. All right. Whoops. All right. So what I was saying is, in the previous program, you saw two different kinds of information flow. So you've probably heard of data flows. So for instance, when this variable endpoint gets used to define this request key, that is an explicit flow or a data flow, because this variable directly influences the value of that struct field. But the more subtle case is implicit flows due to control. So this endpoint variable depends on debug. And the reason is this mutation to endpoint, the push string, is conditioned on whatever this Boolean value is. So it controls whether or not that mutation occurs, and therefore there's an implicit dependency. And so you can think about dependencies or information flows as sort of one of these two types. You have explicit and implicit flows. And that's a fine way to think about it. But I also want to give you a second perspective that's a little closer to how we think about information flow in the theory of programming. So we say that a variable x has an information flow to y if x can cause a change in the value of y. The term information flow itself comes from information theory, where if you learn something about y, you can ask how much you learned about x. But I think it's more useful to start from a causality perspective. And so as an example, let's say we have some black box program P with two Boolean inputs, x1 and x2, and then some Boolean output y. We don't know what P is, but what we want to do is run experiments to say, does x2 have an information flow to y? And here's one possible experiment where we could say, let's say x1 was 0, x2 was 0, and then y was output as 0. Then we changed x2 to 1, and then y was still 0. So this would be evidence that x2 doesn't affect y, and therefore there is no information flow if we changed x2 and nothing happened. Conversely, if we changed x2 in this other alternative program and then y changed, that would be evidence that x2 does have an information flow to y. But we also have to sort of be good scientists in setting up these experiments. So for example, if we ran another experiment where we changed x1 and x2 at the same time and saw that y changed, we wouldn't be able to definitively deduce that x2 has an information flow to y because either variables could explain that change. So one way to think about the definition of information flow is it boils down to running a good science experiment. And what that means a little more precisely looks like this. So this is a sort of mathematical definition where we say, given some program P and variables x and y, if there exists some initial states written as sigma 1 and sigma 2, so those would be like assignments to your inputs, x1 and x2, and there's some final states after we run the program, so that would be your value for y, and we have this condition where if we change x in between the initial states, but we keep everything else constant, and then we find that y is different between the outputs, that is sufficient to conclude there's an information flow. So again, it's just being a good scientist. You say, if I run an experiment and I hold all my variables constant, except for the one thing I'm trying to test, and that independent variable affects my dependent variable, then I can establish there's some kind of causal relationship. There's some sort of information flow. And again, I think this is just sort of an interesting alternative perspective that's very like black box, but this is how theoreticians like to think about information flow. And if you try to make formal proofs that I'll mention at the end of the talk, they tend to be sort of this form. All right. And so that's the definition of information flow. Bringing this back to the two applications, the idea is that information flow is a primitive of higher level program properties. So for example, the slice is the set of variables that contain an information flow to a given variable. So like for all variables y, such that y flows to x. And then an information flow control system wants to check that there are no information flows from secure variables to insecure variables. That's what our thing was catching when it saw that our request secret was flowing into some insecure sync, like our logging framework. All right, so that's information flow, a bit of a mathy slide, but I wanted to give you all a proper foundational sense of what it means to have a dependency in a formal way. So in the next section, I'm going to talk about Flowistry, which is how we implemented a program analysis that computes information flows in Rust programs. And rather than covering the entire analysis, I'm just going to focus on, I think, the two most interesting parts, the two core issues where we could leverage some of Rust's unique features. And to start, we're going to use this function as a running example. So let's walk through it. This copytail function takes a reference to a vector v and an index max, and it copies all of the elements from index 0 to max into some new vector. So it says create a new vector v2, and then for index I and a pointer to elements x in v.iter.enumerate, if we reach max, we break the loop. Otherwise, we push the dereference of x into v2 and return that vector. Fairly simple code. I realize some of you might write this more idiomatically in other ways with various iterators, but this is sufficient to illustrate some interesting aspects of Rust. The information flow that we care about in this program is from v to v2. We want to know that the input v influences the output. And in particular, we want to know two things. We need to determine that x points to a value within v. I'll call this the pointer problem. And push mutates v2 using x as input. Because, for example, if x pointed to a different value that wasn't v, then v wouldn't be responsible for affecting v2. And if push didn't mutate v2, how do we know that push isn't any different from like the length method, that it might just read v2 instead of mutate it, right? That's a mutation problem. And we have to be able to solve both of these problems in order to deduce that there's an information flow. And now, as you saw earlier in the demo, we want to be able to drop into an arbitrary code base and answer these questions within a matter of seconds. And under that standard, there's a number of solutions we can rule out as impractical, thinking about the design space of program analyses. So one option might just be, let's just say we're only going to analyze Rust programs that don't use references or mutability, but that's not really satisfying because Rust is not Haskell. Most people use these features. Another option might be we could have all of these users annotate their functions with their effects, like push mutates v2 specifically or something like that. But for a dev tool like this, that's not practical. It's not going to scale. We don't want people to have to do work just for the tool. Also not reasonable. Another option is we could run the program and see what happens. So you could, if you had it, for instance, instead of inputs to copytail, you could run it and see, all right, I see that this function is mutating v2. I see that x points to v at runtime. And you could do that dynamic analysis, but it's sort of impractical for a lot of reasons. First, you have to construct one of these inputs. Second, you have to run it, which can be slow depending on the size of your application. It can be impractical to run your code if it's supposed to run on a very specific target or you're cross-compiling or something like that. And if you don't you may not have 100% code coverage. You might actually miss information flows that would exist at runtime. So it's important to be able to do this statically without executing the program. And so if we can't do any of those things, it seems like our final recourse is to look at the source code of the functions involved, right? I should be able to look at vec_iter and see it returning a pointer to the vector. I should be able to look at vec_push and see it mutating the vector. But even that is not necessarily ideal, because that's what's called whole program analysis, where we'd have to look at the definition of every called function transitively to determine its effects. That can be slow in of itself. It can be challenging if we don't have access to the full source of our dependencies. And so for those reasons, we would prefer something even more modular, where we don't need to look at the source code of the dependencies. All right, so that's the problem we set up for ourselves, right? How do we compute information flows involving stuff like pointers and mutation, but without allowing ourselves to any of these other solutions that might solve the problem? And another way to restate that in slightly more precise and formal terms would be, we want a modular static information flow analysis with no additional annotations. And the key insight behind Flowistry is that memory safety analysis, or as you might know it, borrow checking, solves similar problems to information flow analysis. And ownership types in Rust are a mechanism to enable modular static memory safety analysis. So like borrow checking already satisfies the sort of technical constraints that we care about. And so that means if we can take the ideas inside of borrow checking and then apply them for our uses, then we can achieve all of the same ends. We can satisfy our technical requirements. All right, so now let's dig into the specifics of what that actually means. So first, we need to talk about memory safety. I realize this is familiar to many of you who have learned Rust, but I'm going to go through it a little bit in detail because it's somewhat important for this talk to understand how the borrow checker works. So just as an example, we're going to modify the program you just saw. So instead of copy till, it's now drain till. And we've added this line of code, v.remove 0, which is deleting the 0th element of the vector as we're iterating through it. So this program is actually quite dangerous. If you were able to run it, you would get a seg fault. And that's because the code has two simultaneous references to the vector v. It has x, the iterator, and then v itself. And if it allows v to be mutated through one of those aliases, that could lead x to point to deallocated memory. And thankfully in Rust, when we try to compile this program, we get some kind of error. Specifically, it says, cannot borrow v as mutable because it is also borrowed as immutable. And the details of the help are actually quite salient here. It correctly identifies, because we immutably borrowed v here in this for loop, and then we tried to use the same data here, v.remove, and mutate it, that's a conflict. And so think about that a little bit carefully, right? Rust understands that there is a pointer to v that is live on line 6, even though it doesn't actually say it, interestingly. It doesn't point to x, even though x is the live pointer. And Rust understands that remove could mutate v. It's a mutable borrow. And so, this might seem kind of simple once you see it in the right way, but that's the basic idea. The Rust borrow checker has to understand what points to what and what operations could mutate which data in order to check for an invalid use of references, in order to do borrow checking. And so that's the sort of mechanisms that we're going to apply to our context. And specifically, the way that the borrow checker is working is this idea of ownership types. And so ownership types boil down to two language mechanisms, which I've illustrated here by expanding out some syntactic sugar in our buggy program. So specifically, every pointer type and pointer expression in this program is annotated with two things. The first is a lifetime, written as alpha or beta, or you might see it in Rust sources like tick A or tick B, that indicates how long the pointer will live. And the second is a mutability modifier, which normally you don't see the no mute modifier, but I've written it out explicitly here so it's clear whether a reference is immutable or mutable. And it's also a very important guarantee that unlike other languages like C++, the no mute modifier is transitive. So if you have an immutable borrow of something, nothing accessible through that reference can be mutated, with the exception of interior mutability, which I will get to later in the talk. But again, the key thing is you have these two mechanisms that we care about. Every reference is annotated with how long that reference will live and whether the data under the reference is mutable, transitively mutable. Those are the key things. And so the way the borrow checker actually works is as follows. It says, are there two pointers to V with at least one being mutable? And so we say, yes, there's two expressions. There's one on this line with this lifetime beta. And then there's one on this line 8, with the lifetime delta. Both of these point to V because they explicitly say that they're taking a reference to V. And we know that one of them is mutable because it says here in the mutability modifier, this thing has to be mute. And the reason that we know that this second borrow must be mutable is we derive it from the type signature of the method involved. We didn't need to look at the definition of how vec_remove is implemented. We just know vec_remove says it expects a mutable borrow of the input vector, and so we definitely have to create a mutable reference. It's possible that remove could be mutating whatever vector we pass into it. And then the next question the compiler asks is, do the live ranges of these pointers overlap? And a way to think about it is, what do these like Greek letters actually mean? And here, the live range of delta is just line 8. So this particular borrow is only used on that line. So it's just that one line. And then the live range of gamma, this particular iterator x, is assumed to be the entire for loop because that's Rust's policy for for loop variables. But it's not immediately obvious what the live range of this beta is, because we pass it into this vec_iter, but we're not necessarily certain what vec_iter does with that lifetime. But the answer is it's the same as gamma. It's the same as x. And again, the reason for that is the type signature of the method involved. So if you look carefully at the definition of the iter method, then it uses what's called lifetime polymorphism. So it says it takes as input this lifetime parameter tick a, and it says the input reference to a vector has some lifetime tick a, and the output reference to elements of the vector has the exact same lifetime tick a. And therefore, in this program, that's what allows Rust to know, oh, okay, because x is live on line 8, that means there's an immutable pointer to v that's live, and that conflicts with this call to remove. Okay, I realize this is sort of a little bit involved, but this is actually how the bar checker is working behind the scenes to use the types in your program to check for memory safety. And going back to our practicality criteria, the point of this example is to show that this is a modular static analysis, for an imperative language, right? It satisfies all the criteria we had before. The only downside is that in order to do this, this can require some configuration from the user, right? Like the person who writes the vec_remove type signature has to say whether or not their reference is mutable or not. Sometimes you have to write out these lifetimes when you're defining the type signatures of your methods. But the key thing for our purposes is if people are willing to do this to make the borrow checker happy, which they are, people are willing to write Rust, then we can repurpose those annotations for information flow. That's kind of the clever trick. And that's why this technique is not actually something you can do in any other language. This is something exclusively that you can do in Rust because it relies on the existence of the borrow checker and of ownership types. So specifically, let's return back to the original problem. Our goal was to, if you remember, deduce that there was an information flow from V to V2. And we needed to know that X points to V and push mutates V2. So for the pointer problem, we know that x points to v because x shares a lifetime with v. And the slightly more general form of this is if you have any place or any variable that has a type of and some lifetime t, then what the points to set of that pointer can be derived exclusively from the lifetime. Just by knowing that that lifetime, that is enough to construct the points to set, which may seem a little abstract, but if you look at pointer analysis in languages like Java or, God forbid, Python or other languages like that, there are these huge edifices of really complicated theory that are needed in order to do this with any amount of precision or soundness to figure out what points to what. But Rust makes this really easy because we could just look at the lifetime, and that more or less, there's some details I'm not sharing, but it more or less tells you what that pointer could point to. And then for the other problem, we can say vec push mutates v2 because it takes an and mute self as input. I mean, this is, again, it's not a crazy idea, but it turns out to be pretty effective once you put it into practice. So the general version of this is what we assume that when we call a function, then only the data that is a mutable reference passed as input could have been mutated. Everything else we assume did not change after calling this function. And we assume that all of the inputs to the function were used during that mutation, is sort of what this formal rule is saying. And collectively, these two things make what I call the modular approximation, which is when I'm analyzing information flows in my function and I see a call to another function, how do I know what that function is doing without looking at its definition? And I instead just look at the type signature of the called function, and then I make these approximations. So there's a question of what happens when raw pointers are used instead of references. It's a great question. We basically fall back on a much more conservative analysis, which is if two raw pointers have the same type, then we just assume that they alias. We don't know. One could do one of these more sophisticated things that you would do in other languages like Java and stuff like that. But it's actually not that essential, because one interesting detail here is if you looked into the implementation of vec_iter, it uses raw pointers, right? Inside of vec_iter, they use raw pointers to sort of scan through an array. But they have written their type signature such that you don't have to know that fact. You could just assume they did everything correctly. And if you just follow the lifetime analysis, the points to analysis works out as if they hadn't implemented it with raw pointers. And so there's sort of an important element of the modularity here, which is even if people are calling functions that themselves use raw pointers, so long as they get their type signatures correct, this is a very common thing in Rust, right? If you encapsulate your unsafe code correctly and write the correct type signature around it, then that enables tools like Flowistry to work. Or another way to think about it is like Flowistry works as well as the borrow checker does. If the borrow checker would not be able to check whether you did something correctly or not, Flowistry also cannot check correctly or soundly whether there's an information flow inside of that program. And so the question is, does Flowistry only work in safe Rust? Flowistry only works soundly in safe Rust, meaning it might miss an information flow if you use raw pointers or if you say like write stuff to a file in your operating system and you read that file later, Rust doesn't know that like file paths in your operating system could alias. So there are lots of ways in which effects on unsafe code, effects in the file system outside of the core language features, Flowistry doesn't know for sure, or it would require a sort of bespoke module in the analysis to deal with that specifically, and there's not a general strategy to handle that. And I'll give you some more examples of this in a second, but these are great questions, yes. The short takeaway is that Flowistry tries its best with raw pointers, but just like the borrow checker, it can't be perfect when dealing with code that fundamentally could be doing something totally unsafe. And however, that doesn't limit the effectiveness of the tool when dealing with code that encapsulates unsafe. All right. Just a few more slides, and then we will wrap up, and I will happily take more questions. So I want to briefly talk about the math bits for those of you who are interested. So these are great questions about, I just presented to you an algorithm that claims to compute information flows. You should be skeptical and say, how do I know that I did it correctly? How do I know that it's a good idea? And one form of correctness is what's called non-interference. This is exactly the definition I gave to you earlier, the mathematical definition of non-interference, which is if Flowistry says that this thing doesn't depend on this other thing, then it satisfies that like experimental condition of no matter how we change this input variable, the output variable doesn't change. That's the shape of the non-interference theorem. And so the way that this looks in practice is we can actually prove that this theorem is true for the analysis. And the way we do that is there's this thing called oxide, which is a formal model of Rust. It uses a lot of Greek letters. We encoded the dependency analysis into this formal model of Rust in a style that's called the dependency calculus, which is another thing from sort of PL history. There's some references down at the bottom if you're really curious. We basically wrote the rule in this formal style with kind of within this logically internally consistent way within the oxide model of Rust, and then we could write out a proof that demonstrates that this theorem is true. And this proof essentially says, if you don't use unsafe features, if you're only within the safe subset of Rust, then we are guaranteed to be sound. This is one cool thing I'll emphasize here is this was actually a really handy tool. When I was writing this proof, I found several bugs in my implementation that helped me go back and make the slicer more correct than it was before, because I realized in trying to write the proof that I couldn't because the proof was wrong. And so this sort of formal methods theorem proving approach can be really helpful for these really sort of easy to get wrong kinds of things of like, am I analyzing pointers correctly, or did I approximate this correctly? And I found this a very helpful tool. Now, and again, it's worth noting that as the question emphasized, this is not guaranteed to be sound for unsafe code. And it's also not guaranteed to be sound for certain primitives built on unsafe code, namely those that use interior mutability, especially arcs and RCs. And here's a very simple example to demonstrate that. So let's say you have some arc mutex. So n is an atomic reference counted pointer over a mutex over the number 0. And then we clone that. So we know that n2 alias is n. And then we mutate n2. We say star n2.lock.unwrap equals 1. Now, Flowistry will say, and this line does not affect n. That's what Flowistry will say. But of course it does, right? Flowistry is wrong in this case. And the reason Flowistry doesn't know this is because these two types don't share a lifetime. There's no tick A that's common between these that lets Rust or the borrow checker know that these two things could be aliases of each other. And similarly, Flowistry can't know. There's really no way around it beyond writing a specific analysis to ARCs that says, okay, I get that these two things could possibly be aliases. And just emphasizing, right, in all of the ways that in Rust you have to work around the borrow checker to do things like interior mutability, similarly in Flowistry, those limitations equally apply to the information flow analysis. And this is one of those areas of improvement we're starting to look at in the tool is how do we more robustly deal with this kind of limitation? Even if you are using interior mutability, can we track these information flows over complicated Rust programs? All right. And so this is actually, I haven't even shown you an implementation yet. This is all just the theory of how the thing works and some sort of formal ideas about it. There's a whole compiler plugin that I'm not going to get into. Basically, we looped into the Rust compiler to extract out what's called the MIR. An example of this is shown in the graph on the right. And we wrote what's called a data flow analysis that goes through each instruction in the MIR and computes all these information flows between the various instructions. That's how Flowistry is actually implemented. Overall, the analysis is pretty fast. It doesn't usually take more than a few seconds per function. And there's a lot of interesting optimizations about like use of sparse bit sets and stuff like that, that if you're super interested in compiler performance, feel free to chat with me more about how those worked. But Nonetheless, there's a functioning implementation. It's on GitHub. I'll link you to it later. But I think the really interesting question about the implementation is how precise it is. So what do I mean by that? So soundness is the theorem I talked about earlier. If a program has an information flow, does Flowistry catch that information flow? Precision is the opposite. It says, when Flowistry says there's an information flow, does it actually exist? This is the sort of false positive versus false negative idea. So here we're talking about false positives. How many false information flows does Flowistry find? And of course, like all tools, our tools not perfect. Let me just give you one example. So let's say we create a vector v, and then we call vec get mute, and we pass in a mutable reference to v, and that gives us back x, and then we don't mutate x. So there's no mutations, no in-place mutations that happen in this program. Well, what's going to happen is Flowistry is going to say, oh, you passed a mutable reference to v to get mute. Without knowing anything else, I'm going to assume that that function mutates v. But of course it doesn't. The reason why get mute takes as input a mutable reference is so it can conceptually pass off that mutable permission from the vector to the element of the vector. It's not using that so as to mutate it inside of that method. And so here there's a sort of mismatch between our assumptions and reality. And so if you wrote this program, Flowistry would say there are more information flows than there actually are. And that also means there's not really a formal theorem that can characterize how precise Flowistry is. It's an empirical question. Like, how often do Rust programmers write code that causes Flowistry to be imprecise? And so the basic way we investigated this is we created a version of Flowistry that isn't modular, meaning it actually steps into the definitions of each of the functions and is much slower, but more precise. And it could see like, vec get mute does not mutate the input vector. And so I know that line 2 of that little snippet does not mutate v. So now we have these two things we can compare. Then we analyzed 400,000 lines of Rust code taken from several large Rust code bases. And basically the key finding is, in the vast majority of cases, the modular information flows were the same as the whole program flows. So what that means is you don't actually lose very much information by only looking at the type signature. Or put another way, if a function says it's taking a mutable reference to something, it's probably going to mutate that thing, which probably feels expected to those of you who are experienced Rust programmers. It's not often you find people just like willy-nilly taking mutable references for the fun of it. Usually that stuff will get caught by Clippy anyway if you unnecessarily take too many permissions on a reference. And so this means that this strategy is actually quite effective, more effective than even we were sort of expecting to see. And so this is a fairly precise approximation compared to something that has. So that's a cool experimental result that we found. So we can say that it's sound in the safe subset of Rust, and it's generally precise in practice. Okay, so that's about it. In the end, we've built what I think is a fairly practical system for doing analysis of information flows in Rust, Flowistry. We've used this analyzer to build a program slicer, which is in active use by a few thousand Rust developers. You feel free to check it out on GitHub at willcrichton/Flowistry. We have some ongoing studies about the human factors of the slicer, like whether it actually helps programmers find relevant code in big code bases. There's lots of interesting open questions on the analysis side. How do you deal with interior mutability, unsafe code, external effects, and improving the performance, the soundness, the precision of the tool? We have another open project called Paralegal, where a colleague of mine at Brown, Eustace, is working on fleshing out that IFC concept I showed you at the beginning into a fully blown system called Paralegal that can check for security and privacy violations in Rust code bases, which is pretty cool. But yeah, so that is my summary of Flowistry. And now I realize I will be happy to take any questions. Thank you for listening. Here's the Q&A link if you need the QR code. And I'll keep the slides up so I can page back through as people have questions. Within IDEs, what abilities has Flowistry had for presenting slices for a single variable across different source files in a single window? Great question. And this is something we found in user studies is people, like, they liked the ability to see stuff within a single function, but they did want the ability to track information flows across functions. And so this is something where we're the direct answer is Flowistry does not have the ability to track slices, or the interface does not provide you the affordance of tracking information flows across functions. So if you want to track one variable down 10 layers of API calls, it's not going to help you with that. But of course, that's a real need. And so we're starting to think about what an interface would look like for that. I mean, Flowistry can certainly go down those layers, and we probably want something that sort of iterates with you. Like, as you want to track a variable, we can compute the next layer for you so as to avoid the performance implications of analyzing the entire code base at once. But it's very clearly something that people want. And so it's definitely one of the directions for research we're considering. And it's worth noting also, if you look into the history of program slicers, this is a whole line of software engineering research. Most program slicers were whole program, in the sense of you would click on a variable and it would show you the subset of the entire program that would influence that variable. But then again, none of those tools exist today. And I think part of it was just the logistical challenges of making that ambitious a goal work out in practice. Hence, we sort of scoped down and focused with that modular constraint, and then we're going to iteratively relax it as we can. All right. Second question is about editor integrations. Will this be available on Vim, NeoVim, Vim, not VS Code? Great question. So I don't personally have plans to expand editor support because I just have very limited time as a researcher, and I mostly just implement it for the stuff that I use, which is either VS Code or Emacs. Sorry to everyone out there. However, there is nothing that ties this to VS Code. The way it works is there's a command line binary that outputs a huge JSON data structure containing the information flows, and then that gets interpreted by the front end that handles all the highlighting and stuff like that. So, and if you go to the Flowistry GitHub page, you can see there's a relatively small JavaScript package that defines the VS Code IDE stuff that actually handles the highlighting. And so if somebody is interested in implementing a Flowistry integration for your favorite editor, I would happily support you in doing that. I just don't have the resources to do that myself. There's a sort of separate question of, ideally, this would get integrated into, say, Rust Analyzer and be a part of a language server, and then it would just automatically work across all these contexts. For technical reasons, unfortunately, that's not feasible right now, because Rust Analyzer does not go down to the level of the mirror. So I mentioned on this slide, right? We rely on this mirror data flow representation, control flow graph in the compiler, because this is where the compiler does borrow checking. And we need the borrow checker in order to figure out stuff like the pointer analysis. But Rust Analyzer doesn't do that yet. It only goes down to what's called the here, and it doesn't actually do borrow checking for you. Now that's changing, and I've been pinged by some Rust Analyzer people about some plans for that, but that's all very experimental. I would love it if Flowistry was incorporated into something like Rust Analyzer, because that would solve all of your editor integration problems. But there are some non-trivial technical challenges where Rust Analyzer needs to have feature parity with the Rust compiler in ways that it doesn't have. Going down the list. Are there any interesting research topics or projects of Rust lately? Yeah, great question. There's a good amount of research happening around Rust within academia. So I represent probably the more human-centered side. There's a decent number of people focusing on what makes Rust hard to learn and how do you create more usable tooling and libraries and stuff like that. For instance, a project that I'm working on right now that some of you may have actually seen is the Rust book. So I'll paste this into the Zoom chat. So if you go to rust-book.cs.brown.edu, then this is basically an experiment on how do you make the content that people use to learn Rust better in a scientific way. So we're using quizzes to sort of iteratively get feedback on what people find most difficult in Rust and that sort of thing. And then go back and make changes to the book and see if it improves learning scores. I'm actually giving a talk about this at RustConf in September. titled The Art and Science of Teaching Rust. So if you're interested more in that side of things, you should check out my RustConf talk. I'm sure they'll put up a recording at some point if you can't go to Albuquerque. And expand on human-centered. Human-centered just means like thinking about, maybe by contrast, let me give you examples of research projects that don't really center humans. So there's a lot of work on verification. There's the Connie verifier, there's Crusoe. If you look at the Rust formal methods interest group, there's a whole community of people who are looking at things like, how do you prove theorems about Rust programs? How do you use SMT solvers? How do you formally verify that a Rust program does what it says it's supposed to do? And that's not really, I would say, human-centered in some sense. It's very technical work, but totally very interesting space. Another category of research is automated transpilation of C to Rust. So there's a lot of folks working on how do we produce idiomatic Rust from a C code base, as opposed to just like big globs of unsafe code. That's a really interesting direction. Some folks are looking at vulnerabilities in the cargo supply chain. How do we know which crates are the most vulnerable to being attacked, and who's using unsafe incorrectly? It's another very popular research topic. So those are kinds of things you can find published in academia. And then the human-centered side is people who focus more on user experience, like Flowistry in the IDE as the developer tool is a very human-centered thing, because the purpose is to help you understand a piece of it doesn't like do anything at runtime. Flowistry isn't sort of like a library that's intended to check your Rust code or whatever. Or I guess the IFC stuff is a little more, but at least the IDE tool is just a purely human-centered thing, because it's only about helping you as a person understand what a Rust program is doing. Can you go into more detail about how IFC works? Yeah, sure. So information flow control, very long history of research. There's tons of ways one can approach it, but the basic idea is you tag which data types are secure. So you say like, this is a password, this is an API key, this is something is very secure. You tag which operations or data types are insecure, like this logging thing goes to a public output, or this thing gets printed to the front page of a website that is publicly accessible. And then you describe policies. So the basic policy is secure things shouldn't go to insecure places, but there are more sophisticated policies you can write depending on the expressiveness of the IFC system, like only people with the right authorization should be able to take certain actions. Or what's another good example? Like GDPR, for instance, it would say, if data is associated with a user, then when the user requests their data is deleted, all the data associated with the user has to get deleted. You can't forget to delete some aspect of their data, is another kind of policy that these kinds of systems like paralegal might ideally handle. Now, but I'll emphasize, all of this is very researchy. There have not been, this is like 20 years of research, but no one's really come up with a practical system yet, which was also true for program slicing, hence my interest in this area as a researcher. And so there's not really a standard for what IFC is, but there's just a lot of design points. And the general idea, though, is catching security and privacy bugs by making sure, secure things don't fall into insecure hands. I see, is there a compromise you can do where you pre-compute the behavior of standard library functions with the higher precision non-modular checker to solve the vec get mute false positive you mentioned? That is a great idea. Yes is the short answer. So there's a sort of version of Flowistry where you would compute, the technical term that's used in the literature is a procedure summary. So you would summarize the information flows that come out of a function. So for instance, you'd say like vec get mute does not mutate its input, but the input vector flows to the output pointer, right? Would be the sort of basic facts. And so that is a totally feasible implementation strategy where you could generate these procedure summaries. You could like cache them or memoize them for very commonly used stuff like the standard library, and probably get a higher precision analysis. And so, one of the many optimizations that haven't had time to implement, but is a great idea if someone would be interested in trying to make the system a little more precise.
rusteastcoast.com is our link tree to gain resources and links to things mentioned in this talk, and to join the Discord and participate in upcoming events. Thanks for joining us tonight.